Khaja, it's there, it should be there. Manny, you should have it. Om, you should have it. Prasad, who are you logging in from NH? The video link for the last class. Okay, I did send it to some people, so let me just check one of the, yep, this is one of them. Oops. All right, this is the link from yesterday. Anybody else requires it? Before I get started, it becomes really cumbersome after that. All right, done. All right, guys, let's get started. The plan for today. Amanda, I gave the permission, check again. The video link for yesterday's class is there as well. That HTTPS link over there. So if you haven't received it, you didn't record it yesterday, that's the link over there. So the plan today is to take a look at GRE and IPsec, GRE IPsec in tunnel and transport mode, native IPsec tunnel, MGRE, and DMVPN. That's the plan for today. If you take a look at your outline, my objective today is to knock out this portion over here. Pen pop in. We did this yesterday. We're going to do this, this, and DMVPN today. All right, that's the plan. So let's get started. I'm going to launch my GNS over here, set up a simple topology with 3 routers. Router 1 on one edge, 2 in the middle, and R3 on the other side. Let's say this is my site in Dubai, and this is another site in London. And this person over here is the acting ISP. I'll connect my sites to each other, connecting to the ISP. London connects up to the ISP, and I'll launch the routers. The notes, no, I haven't. What I'll do is at the end of the class tonight, I will send both. I'll get a mailing list going tonight for all the class, all the people that have signed up. So I have everybody's email, so I can send you an email at the end of the class for the notes as well. All right, so this is my network that I'm going to be configuring. This is my public address on the internet. This is the public network for the London router. On both sides, I have some internal networks, which I'm going to simulate by loopbacks over here. And I want you guys to help me out with the configuration that we did yesterday in terms of the GRE tunnel to connect R1 and R3 to each other as if they're directly connected to each other. All right. So to start configuring this over here, I'll connect to the 3 devices. Router 1 being the Dubai router. I'll say 10.1 is my public IP. This is the IP address assigned to me by my ISP. Then I have my internal network, which is going to be simulated by a loopback. I have another internal network, also simulated by a loopback. And I have a default route pointing towards 10.2, which is router 2. Good so far? So if you take a look at your interfaces, they're right there. 10, 172.16 as the inside, and the 192.1.10.1 as the public side. This is the ISP. This is the network towards R1, Dubai, and this is the network towards, what did I call it, 10 and 20, right? Yep, 20.2 on towards R3. These are the 2 interfaces that I have in my routing table, 10 and 20. R3, 20.3. On the public side, loopback 0 is 10.3.3.3. And a default gateway, 20.2. So if everything's fine, I should be able to ping the public address of my other router in Dubai. Everybody follow and understand the topology over here before I start doing the GRE part of it. Everybody good with this? Yes? All right, so if everything's fine, everybody's fine with this, what I'm going to do is I'm going to set up a tunnel interface to connect R1 to R3. When I create the tunnel interface, which we did yesterday, the default encapsulation on the tunnel is a GRE point-to-point tunnel. Point-to-point means only one destination. That's the default configuration of a tunnel interface. So let's set that up on R1. Do you guys remember how we did it yesterday? Help me out. Normal GRE. On R1, how would I configure it? Interface tunnel 1, tunnel source, tunnel destination, and then the IP address of the tunnel itself. So the network that connects R1 and R3 together, logically, is going to be 192.168.1.3. So this network that I'm creating over here, I'm assigning it an IP address of with this guy being .1 and this guy being .3. Good so far? So let's do that over here. I'll put the same config on R3, reversed. Now, one of the things I can also do if I want to, when I specify my source, rather than specifying the IP address of the source, I can also say, get the IP address from the S00 interface. So whatever the IP address of S00 is the source address. So rather than typing in, you can also do that. Destination, you need to type in. And then my IP address is going to be on the same network, different IP. So I can just copy this onto R1. And copy this onto R3. If I go into my routing table now, you will notice that I have a new interface created over here. What is it called? It's called 192.168.1.1. So technically, I am directly connected to a network, a tunnel network 192.168.1.0. And if I take a look at the tunnel interface itself, show interface tunnel 1, you will notice the protocol is GRE. So it's a GRE interface, which is the default. And the tunnel source is 20.3. The destination is 10.1. Any packet leaving the tunnel interface, which my routing table says go through the tunnel, will use what? This as the outer header. So right now, if I ping, let me do a show IP route over here. Let's say I type in on router 3, I'm going to type in ping 192.168.1.1. It immediately says, let me check the routing table. Where do I need to exit from? Sees 192.168.1.1 is directly connected to me. One second, guys. 53. All right. So it checks 192.168.1.0, the same destination network, says, okay, I'm going to exit from this guy. So my source address is going to be my tunnel interface. Destination, I'm pinging this guy. So I need to put this as the destination. But at the same time, it sees that the destination is going via the tunnel. That's where it goes back up over here and checks what? How do I exit the tunnel? The tunnel says it's a GRE tunnel. The tunnel should have this source and this destination. Puts an outer header over here. The outer header looks like this. Source and destination. So the source is 20.3, 10.1. So this is your GRE packet. And this is going to be, if I'm doing a ping, it'll be whatever I'm using as a protocol. In my case over here, ping is ICMP. So that's what the packet looks like, and it gets sent. On router 2, it only checks what? This header, the GRE header, which is 192.120.3 going to 10.1. It is aware of it, forwards it. Although it does not check this one, it will be in the clear. If I'm running a sniff, I will be able to see this packet. All right, let's do that. Let's check that first. So this is pure GRE at this point. Before I do that, let me go ahead and run my sniffer. No, not the physical IP, whatever you specified as your tunnel source and tunnel destination. That's the whole purpose of this guy. In my case, I'm using the physical IPs, but if you had multiple internet connections, I could also use it as a loopback. So whatever in your configuration you use as a source and destination is what is being used. The public IPs is generally what's going to be used. A better word for it. Yes, the public IP. So right now, there's nothing over there. If I go to my router and I ping 192.168.1.1, which is it's a private IP. It's going to be tunneled within the packet. My ping works. If I look at my sniff over here, this is my ICMP echo that was sent. The outer header has 20.3 going towards 10.1. This is your GRE packet, and then you have the IP packet, which is the ICMP packet. Echo request. And then this is the response that you get. Request, response, request, response. I see all the packets. But I can actually see the packet. If you ever wondered what the ping looks like, this is the data portion of a ping. This is a junk that it sends in what? In your ICMP packet. The 000 DV, whatever, ABCD, ABCD. All right? But I have set that up. I have set the network up so that R1 and R3 are now directly connected to each other. Can I run a routing protocol at this point between R1 and R3 over the internet to route these private addresses? That's the whole purpose of what? GRE. It's a VPN that allows me the ability to connect two private networks over a public network, and it's actually over a tunnel interface. So because it's logically connected to each other, I have the ability to run a routing protocol, let's say EIGRP, RIP, OSPF, whatever routing protocol I want to run, I can run it. I can run it to enable it on the internal networks as well as on the tunnel, so I can run the routing across. So when a EIGRP update is run, because I'm enabling it on the 192.168.1.0 network, it's going to send an update from router 1 to 224.0.0.10, which is the multicast for EIGRP. But because it's going over the tunnel interface, it's going to be encapsulated in a unicast packet, which will have this as the outside header. Why? Because my tunnel interface has this as the tunnel source and tunnel destination. Everybody okay with this? So let's run the routing now. So router 1, router EIGRP 100, no auto, network 10, 10.0, and 172.16.0. One second, guys. Anybody else require record permissions? I think everybody else has it. I gave it already, Abraham. Check. All right, so I can ping it. I ran the routing over here on router 1. Now I'm going to run it on the other guy. So the neighbor is up, show IP route EIGRP. I can see the 10.1 network. I can see the 172.16.1.0 network. And if you take a look at this packet now, the EIGRP packet is coming over here. See this hello packet is an EIGRP packet from 1 to 224.0.0.10, which is EIGRP. You can actually see the EIGRP packet. It's the outer header, inside header, EIGRP inside. Everybody okay with that? So I would also add what? Router EIGRP config over here. Good. Now, the advantage, what's the advantage that it has over what we did before this, prior to this, the IPsec LAN to LAN? What's the advantage that I gain over here? Dynamic in the sense of what? If new networks get added into your network, it's much easier to add what? That network into my setup because of dynamic routing, all right? The ability to run a dynamic routing protocol to advertise new networks. All right, good. Disadvantage. The inner header, inner packet, although is encapsulated, it is sent in the clear, so it's not secured. People can see it. As I showed you, you can actually see the inside packet. Everybody good with that? It is point to point in terms of what? The outer header. But it needs to traverse through a network in the middle, which is not yours. It's a public network. That's the whole purpose of a VPN, to connect two private networks over a public network. Now, why could I not run this in the previous setup, what we did yesterday? Why could I not run a routing protocol with IPsec? What was the problem with that? There was no tunnel interface. Absolutely. There was no interface basically connecting what? The two edge points to each other directly. It was connected, but it was logically connected via what? It was logically connected via that policy. The policy was that ACL that said any traffic coming in from this network to that network should be encapsulated. So the drawback over here is that it's clear text. So to counter that, one of the things that you can do is combine GRE over IPsec. Basically, what I'm going to do in this type of setup is take the GRE packet and encapsulate it within an IPsec packet and encrypt the packet. So I'm going to take whatever goes over the tunnel and encrypt it using IPsec. So yes, let the dynamic routing run, but I'm going to encrypt the dynamic routing. Okay? So I can counter that disadvantage that I had with what? With GRE. GRE was giving me dynamic nature, but it was clear text. So to counter that, what I'm going to do over here is I'm going to take IPsec and tell it I want to encrypt any packet that leaves the tunnel interface. So I'm combining GRE and IPsec. But before I do that, I want you guys to take a look at this packet over here. What's the size of this packet and what does the packet look like? What's the size of this hello packet that is getting sent every 5 seconds? That's your EIGRP hello packet. Take a look at it. What's the size? It is 88 bytes in size. So just to give you a crude show of the packet, I'll say it's a GRE packet. It has a source of what? 192.1. Let's say 10.1 going towards 20.3. And then inside the packet, you have your EIGRP packet that has a source of this guy going to and its data. This is what the packet looks like right now. Kinda, right? And what's the size of this packet? 88 bytes. Everybody agree with that? You guys understand that? So now what I'm going to do with it is I am going to encrypt this packet using IPsec. Do you guys remember IPsec from yesterday? The different steps that I did to set up IPsec. What was the first step? Let's follow that. Help me out with the first step for IPsec. Phase 1. Crypto ISACamp policy 10. Auth pre-share. We haven't done certificates yet. Hash, let's say MD5. Group 2, encryption, triple des. As an example, I need to match it on the other side. Whatever I specify one needs to match on the other for this phase. Because I said my key is pre-shared, so I'll set the key up. Address is, I'm on router 1, so I'm going to point to the public address of router 3. Everybody okay with phase 1? Yeses, please. This is again from yesterday. Good. Now let's go to 2. Crypto IPsec transform set. Give it a name, whatever you want to call it, ABC. Triple des, we'll say SHA. Good. Normally, yesterday, what did I do after phase 2? So phase 1 is set, the session key is established, sends it to phase 2. Phase 2 sets up your encryption and hash for phase 2. The next thing was the ACL, because that defined what traffic needed to be encrypted. Here, I'm telling it, any traffic leaving the tunnel should be encrypted, so I don't need an ACL. So I'll skip the step. I'll create another step, and I'll tell you what the use for that is in a bit. Configure an IPsec profile and attach the transform set to it. Crypto IPsec profile, give it a name, whatever you want to call it. iProf, just a name. Set, transform set, ABC. So iProf is calling the transform set. I'll tell you what that step does, but I don't need an ACL because of what? Anything that leaves the tunnel interface in this type of setup will be encrypted. Any traffic leaving the tunnel interface should be encrypted. Okay so far? Now the last step over here, oops. Step 4, assign the IPsec profile to the tunnel interface. Before I do that, do you guys remember the crypto map from yesterday? Crypto map ABC 10 IPsec ISACamp. Do you guys remember this? Match address 101. That's the interesting traffic ACL. Set peer. Set transform set. Isn't this what my crypto map looked like yesterday? Yes, everybody? Yep. Now, take a look at the 3 components of the crypto map. What are the 3 components of the crypto map? The first one, ACL. It defined what traffic needed to be encrypted. Agreed? What did I tell you over here? Any traffic leaving my tunnel interface will be encrypted, so I don't need an ACL. It's an implicit thing. Any traffic leaving the tunnel should be encrypted. I don't need to specify that. So I don't need an ACL. What's the second thing over here? Set peer. right? Now, take a look at the peer. Don't I have a peer on the tunnel interface already defined? The tunnel destination is my peer. Tunnel destination is my peer address. So I don't need that either. You remember, this is the tunnel interface. It already has a tunnel destination. That is my peer. It's a point-to-point tunnel. So I don't need that either. So what's left then? The transform set, right? Haven't I linked the transform set somewhere? Where did I link the transform set? I linked it up to my profile. So what I'm going to do on the profile is this. Interface tunnel 1, tunnel protection, IPsec profile, iProf. I don't need a crypto map. So what I'm saying with this command is any traffic leaving this tunnel interface should be protected, which means encrypted, by using the profile called iProf. And what does iProf contain? The transform set. I already have the tunnel destination. I already have my, all traffic encrypted. So the only thing that was missing was what? The transform set. I applied it. So at this point, any traffic leaving my tunnel interface will be encrypted. You guys understand that? So I've broken it down into what? 4 steps that are required to set up encryption on a tunnel interface. So now I'm encrypting my GRE tunnel. This is called GRE over IPsec. Let's see if it works. Copy it. I'll go to router 1. Paste it. The commands took. So I'm encrypting on my side. It says received a packet that was not an IPsec packet. It was expecting a IPsec packet. Now one side is encrypting, the other side is not. What should happen to your EIGRP neighbor relationship? It's gone down because one side is encrypting, the other one is not. So how do I bring it up? Configure the same thing on the other side. So R1 was this guy. On R3, this part remains the same. The only difference is I'm going to change the address to 10.1 because 3 is going to point to 1, the public address of 1. Phase 2 is the same. The profile is the same. Apply is the same. So copy it. Let's go to R3 and paste it. My tunnel comes up. My traffic, my interesting traffic is my EIGRP hello packets. It brings my ISACM tunnel up. It brings my IPsec up. Everything is now encrypted. QM idle, it's already come up. What is interesting traffic right now that brought it up? The interesting traffic is your EIGRP updates. So notice the EIGRP hello packets are getting encrypted and decrypted. So if I keep on doing it, this number will increase because every 5 seconds, I'm sending an EIGRP update. So I have set up GRE with IPsec over here. What did I have to do? Once my GRE tunnel is up, I basically enabled IPsec on it by using these 4 steps. Phase 1, phase 2, just like you did yesterday. Create the IPsec profile, apply the profile to the interface. I'm done. Absolutely does. And you can see that. Now, remember this 88? I was sending a hello packet every 5 seconds. Let's go down and check this. Notice there's packets going across even now. But I don't know what they are. They're just on a regular basis, these 140 packets every 5 seconds are being sent. These are your EIGRP updates. But it just says ESP over here. It doesn't show you anything. 20.3 to 10.1, ESP. That's it. This is your EIGRP hello packet. But take a look at the size. It has increased to what? 140 bytes. What was the default? What was the packet size before? Remember this? What's happened to this packet now is a new ESP header, which basically takes the same source and destination from where? From GRE, and puts it up. This extra header of ESP, which has taken the outer header, now the entire GRE packet becomes data for what? For ESP. This size, this additional size is 140 bytes. So what is the IPsec header then? You guys agree? The initial EIGRP hello packet, which was my base packet, was 88 bytes. Now with the addition of the IPsec header, it's gone to 140. That tells me that ESP header that has been added is a 52 byte header. So what's the drawback of doing encryption over here? You have increased the size of what? The packet by 52 bytes. That becomes your ESP header. Everybody okay with this? Any questions at this point? Everybody understanding this so far? So far, so good. Brilliant. Now, let me explain another aspect of it, which is also important over here, is the transport and tunnel mode. Do you guys notice that the ESP header and the GRE header is the same? Same source, same destination, right? Now, by default, IPsec takes the packet and goes to work and adds the new header. This is done in the tunnel mode, which is the default. What a tunnel mode does, it says whatever packet I'm going to get, I'm just going to slap my header on it and send it across. Whether there's duplication or not, I'm going to take the packet as is and send it across, which is known as the tunnel mode. By default, IPsec runs in tunnel mode, which takes the existing packet coming in that needs to be encrypted and sends it across by slapping the outside header to it. Whether it's duplicated or not, it doesn't look at it. You can check and see if it's done running tunnel mode or another mode that I'm going to talk about in a second in your configuration or your show output. If you do show crypto IPsec SA, you'll see that in use settings is equals to what? The tunnel mode. This is the default. Make sense, guys? Everybody okay with this? Double header side change with the type of encryption, with this type of encryption, yes. In this type of setup where I have the GRE inside and I have the ESP header being the same, I have the ability to run a mode known as a transport mode. You do have the ability if your inside header and outside header are the same, and it generally only happens with GRE and IPsec, you have the ability if you have the ability to run, actually I should write it like this, you have the ability to run IPsec in transport mode if your inside header and the outside header are the same. What does that do? In transport mode, it will remove the duplication of the IP header and make the packet a bit slimmer. What do I mean by slimmer? Smaller packet. So what does that packet look like? Let me show you that. By the way, this is known as tunnel mode. In the transport mode, it will keep this header. It'll still be a GRE packet, but it will get rid of what? The duplication. So now I'll say what? ESP outer header, source destination IP GRE, but not the duplication, not another 10.1 and 20.3. And this takes off 16 bytes over here. It shrinks the packet by 16 bytes. So now the packet size will be 124 if I change it to what? Transport mode. What's the default mode? You guys saw that. It is what? Tunnel. How do I change it to transport mode? The way I change it to transport mode, do you remember this when I created my transform set? It puts you into a subconfig mode over there. You put in mode transport. That's how you do it. So if you know that your GRE is running and IPsec is running, it's going to have what? A duplication of header. Let's make it a little bit more efficient. I have the ability to run it in transport mode. The default mode is tunnel. All right, copy it. We need to do it on R3 as well as on R1. But for it to take effect, I need to clear crypto SA. So it restarts the process. Otherwise, it's still going to use that for the next hour. Why is it called GRE over IPsec? Because I'm running a GRE packet over an IPsec packet. Over meaning it's basically an IPsec packet which is carrying the GRE packet. Have you seen a truck, Deepti? What does it carry? Goods, right? So the goods are on top of what? The truck? Who's carrying it? Okay, truck is your ESP. Don't get caught up in these type of things. But that's what it is. It's GRE over IPsec. Because it's carrying your GRE packet. All right, so once I clear it, show crypto IPsec SA, you'll notice that the mode has changed to what? Transport. Now, if I go back over here and check, take a look. See that packet, the recurring EIGRP hello packet? Now is the size of what? 124 bytes. Why 124 bytes? I've shaved off another 16 bytes for what? For the duplication of the header. Good so far? Everybody okay with this? So you guys understand the difference between tunnel mode and transport mode? Yeah? So most of the times, unless you're running GRE over IPsec, you're going to be running tunnel mode. The time you're going to run tunnel mode is when you're running GRE and IPsec together in GRE over IPsec type of setup. You want to set it up based on transport mode to make it more efficient. It's not going to work. It was working before as well. It's a little bit more efficient. You get my point? So with transport mode, you're making it a little bit more efficient. Otherwise, it's still going to work. Having said that, when you set the mode to transport, it takes a look at your setup and sees if transport is the proper mode for this type of setup. It will only run it based on that. It's not going to take your configuration blindly and use it. It's intelligent enough to see if I'm not having the same header inside and outside, it will automatically move back to tunnel. You cannot use it in site-to-site IPsec, transport mode. Why not? When you have normal IPsec site-to-site, what does the packet look like? It doesn't have that third header. The normal packet looks like what? Your inside header, let's say 10.1.1.1, going towards 10.2.2.2. This is normal what? IPsec LAN to LAN, what we did yesterday, right? And what's outside? The outside header. There's no duplication. So in this case, if you set transport, it'll say, oh, he doesn't know what he's doing. It will default back to what? Tunnel. So your configuration will say transport, but it's going to be set to tunnel. So transport is only useful if you have that duplication with public and your EIGRP, not EIGRP, GRE and ESP. Understand that, Zahir? So on a normal site-to-site, it's not going to work. Now I'll show you something else, and you'll see that it doesn't work if you have no duplication. It is intelligent enough. Why did I need to run GRE? By the way, before I go on, just to make sure you still see GRE over here, it's still a GRE tunnel. Show interface tunnel 1. Notice the packet still has the protocol as what? Tunnel is GRE. Why do I need GRE? Can't I run IPsec on the tunnel interface without running GRE? How? When I created the tunnel interface, it was created as a GRE tunnel. I don't want to run GRE. I want to run it just as an IPsec tunnel. Does IPsec support routing? Why not? Why doesn't IPsec support routing? Well, can I run this tunnel interface as IPsec? This tunnel interface that you create generally by default is running what? GRE. But that doesn't mean I cannot run IPsec on it. If I want, I can change the default encapsulation of this interface to IPsec. So I'm going to run IPsec, not GRE on this tunnel interface. So I can run a tunnel interface as a pure IPsec interface, eliminating GRE completely. It's a native IPsec tunnel interface. How? Very simple. When I created the tunnel, remember I said tunnel source, tunnel mode, tunnel source, tunnel destination, all that. I can also do this. When I do that, I'm telling it, I don't want to run GRE. I want to run this as an IPsec tunnel interface. It's native IPsec tunnel interface. Same thing over here. It's gone down because one side is running it and the other one is not. What did I do over here? I changed the protocol from where? From GRE to a pure IPsec tunnel interface. If I now go into my interface, the protocol is no longer GRE, it's what? IPsec. So in this case, I really did not need to run GRE. I could technically have done IPsec from the get-go, but I wanted you guys to progress from the tunnel mode to the transport mode to see how you can run IPsec on a tunnel interface natively without running GRE. And what's the advantage? Well, the advantage is I also eliminate this GRE header, which is about 8 bytes. So now the packet will look like this. Native IPsec tunnel interface. This is also known as static virtual tunnel interface. So what does that packet look like? Exactly the same. GRE is gone. So it's now going to be 116 bytes. Now, Kaushik says, can we remove the transport mode also? Now, the transport mode over here is useless. Why? There's no duplication. Now, this is the packet. This is the way the packet looks. There's no GRE. There's no GRE header. It's gone. So although I did mode transport, remember what I was telling you. It's intelligent enough to see that, hey, this is not transport. There's no duplication over here. I need to run it as a tunnel. So although I configured as tunnel, it's going to run as, sorry, I configured as transport, it's going to run as tunnel. You'll see that, but I want you guys to see this first. So let's go back over here and check the size. Do you see that? I'm shaving off bytes over here. So I've shaved out 24 bytes. That's all I can, but that's still good enough. From 52 bytes header, I went down to a 24 byte header. Or shaved out 24 bytes, 28 bytes is still there. You guys understand that? And if I go over here now and do the show command, it's tunnel. If you look at your show run, although I've configured as mode transport, it says no, it's not mode transport. So it is intelligent enough to see that it's not mode transport. Don't put it in. Kaushik's right, you should remove it. But I want you guys to see, even if I put it in, it does not have any effect because it knows that the inner header and the outer header are not the same. So I cannot remove it. I can only remove it if there's duplication. That is in case of GRE over IPsec. So from this point on, whenever you go to run and you want to run a tunnel interface for dynamic routing, don't run GRE, just run a tunnel interface, but run it as native tunnel with IPsec. So no more GRE over IPsec, at least not for point-to-point. Well, it depends on what the question is asking. If the question says, what do you call it? Run it as a native and you do not do the tunnel mode, yes, you're right. You're going to fail. Depends on the question is what the question is asking. You need to take a look at that. Everybody okay with this? How did I do it configuration wise? R1 interface tunnel 1, tunnel mode IPsec IPv4, R3, same thing. Now this is step by step, right? If I had to do it from scratch, let's say I was configuring it and I knew I was going to do what? The SVTI configuration, native IPsec, tunnel interface. These are the steps that I would do. Step 1, phase 1. Whatever you want to call it, it's just a name. Not with point to point. Not with point to point. I would do it if I'm doing multi-point. I'll get to that after this. Point to point, this is, by the way, GRE over IPsec. Do you think this thing is new that I'm doing over here? At least 10 years old. So this is what you would generally do for what? Native IPsec tunnel interface. If you knew that you're going to do it from scratch. I didn't want to do it like this. The reason I didn't want to do it like this is because I wanted you guys to go through what? The phases. I wanted you guys to understand what transport mode is. I wanted you guys to understand the tunnel mode, see the changes in the packets until eventually getting to this guy. But I could have technically done this off the start, right off the bat. You guys get my point? Understood? So this is SVTI. In terms of point to point, this is my favorite way of doing it, point to point. My objective today was to cover this. We've covered this much already. GRE IPsec, tunnel mode. Everybody good with that? GRE IPsec, transport mode. Native IPsec tunnel, the SVTI. Good point to break, because the next section will take a bit. Now we'll go into multi-point GRE, MGRE, also coupled with DMVPN. That's my objective for the day. Let's take a break. It is based on our reference clock. Let's take it at 6:40. Let's take it for 6:55, 15 minutes roughly. Come back fresh. Very important subject coming up. Any questions so far on this before you guys go? No questions? All good? All right, break time. Hey guys, ready? More yeses, please. All right, let's start with MGRE now. So when I set this tunnel up over here between the two devices, it is a point-to-point tunnel. Whether it was the GRE that I used, whether I was using GRE IPsec, or if I was using SVTI, all the three tunnels were point-to-point. That means when I created the tunnel, it could only have one destination. If I had a large number of sites around the world that I wanted to connect to each other, let's say I had router 4, 5, and 6, and these were other locations that I also wanted to connect up. Guess what? I could not do that because of what? One second. I could not do that. Why not? I could do that. I shouldn't say I couldn't do it, but it would be a scalability issue because now I need to create what? Separate tunnels between what? Each of those entities. Bunch of different tunnels. So the problem with this, whether it's GRE, GRE IPsec, or SVTI, because of the nature of point-to-point, it is a scalability issue. So if you have a small number of sites, if you have a small number of sites, the previous solutions are fine. But if you have a large number of sites or are planning on growing in the future, the existing type of tunnels will cause a hindrance. All right? That's where MGRE comes in. What MGRE allows us the ability to do is allows us to have a single tunnel with multiple points on it. How many people over here have worked with frame relay? Yeah? Do you guys remember in frame relay was a multi-point network, a single network with multiple points on it? And you would do the mapping based on the del C? The del C mappings. Same concept over here. It would be a single network, single multi-point logical network. So let's say this is my internet. I'm going to draw the internet in black. Let's start with 4 sites. Let's say Dubai, London, New York, and let's say Sydney. They're all connected towards what? The internet. They're all connected on the internet. I want them to be part of a single logical tunnel, not multiple point-to-point tunnels. I have the ability to create a logical, single logical MGRE, multi-point GRE tunnel, where all of them belong to the same network. So multiple points on the same logical network. So on the red network, which is the MGRE network, they are on the 192.168.1.0 network, .1, .2, .3, .4, just like I had 192.168.1.0 with .1 and .3. Now I have 4 sites connecting to the same tunnel. Each one of those networks will have their public addresses defined or given to them by their ISPs. So let's say this address over here is 10.1. This is the public address. This is 20.2. Let's say this is 30.3 and this is 40.4. These are the public addresses assigned to them by their ISPs. I need to figure out a way of getting my mappings correct so that whenever somebody wants to go from Dubai to London, London's public address is 20.0 and his corresponding tunnel IP is 1.2. That's what I want to accomplish over here. Let's set this topology up and then we'll take it up from there. So I'm going to get rid of this topology. And instead I'm going to put in, let's put about 5 or 6 devices I need. Router 1, 2, 3, 4. I'll keep 5 on the side. I have a special use for 5. We'll talk about that later. And I have 6 as my internet simulator. So the router 6 is my ISP, the internet over here. Let's connect them up. I'm going to connect 2 serials, so 2 fast Ethernets for R1 and R5. And then I'm going to connect serials for, let's say, 2, 3, and 4. All belong to the same company. Let's fire them up. All right, so let's set the internet portion up over here. This is 10.0, the public network that belongs to R1. This is 50.0, belongs to R5. 20, 30, and 40. These are public addresses assigned to each one of those sites by their respective ISPs. In my case, it's the same one. Let's put some cities over here so we can relate. all around the world. All right? And each one of them has some loopbacks behind them. Let's put them up over there as well. This is the network that we'll be working off of. All right, so let's set this up. To speed it up, what I'll do is I'll do it in Notepad. This is for R6. Ten dot 6. .6. This is S0, which is 20. S01, which is 30. This is 40. Just copy it onto 6. That's my ISP. This is all based on this setup that I did over here. Next, router 1. This is 10.1 for router 1. And a default gateway pointed to 10.6. Let's go to router 1 and set this up. See if I can ping my ISP. Router 2. .20.2. Default gateway 20.6. Should be able to ping 20.6, which is its ISP. Oh, sorry. R2 has a serial interface. Let's check now. There you go. Should be able to ping 1 as well. Let's do 3 now. .30.3, and this is 30.6 as the default gateway. Let's check this, 30.6, which is my default gateway on R3. And I should be able to ping 10.1 and 20.2. Moving on to router 4. .40.6. Should be able to ping 10.1, 20.2, 30.3, and the last guy over here is R5. And on this one, the interface is F. 1 and 5, I kept it as F. .1 should be pingable. 20.2, 30.3, 40.4. One second, guys. All right. So this is taken care of in terms of setting the topology up. I'll close this over here. So my topology is set up. My objective is to be able to connect R1, 2, 3, forget about 5 for right now. We'll just focus on Dubai, New Delhi, New York, and Sydney. We'll bring in London later on. I want to connect 1, 2, 3, and 4 to each other on a single what? Single network up. Why? If I don't do a single network, I do a point-to-point type of setup. The issue with that is scalability. As I scale and add more sites to my network, point-to-point network, it would have to have a separate point-to-point network between each of those sites. You guys agree? You understand what I'm saying? So to get around that, I want to set up a single network where everybody connects into. That's where MGRE comes in. MGRE allows you the ability to create a single GRE tunnel, but with multiple points on it. This is where GRE is being used, not in a point-to-point setup. In a point-to-point setup, I would still use or stick to SVTI. But this, if I have scalability that's required, MGRE, multi-point GRE is the way to go about doing it. I'll show you how it works, but then I'll show you a better way of making it work. So let's say I want to set this up between 1, 2, 3, and 4 right now. How do I connect them up into a single network? Let's take a look. So I'll just put I'll save this file as initial configuration for MGRE DMVPN. So you'll have this file just in case you need it. So going back over here, how do I set up MGRE? On R1, I'll create a tunnel interface, IP address of 192.168.1.1, tunnel source. Now tunnel destination, this is how I would create a point-to-point tunnel. Here it's not possible. Why? In a point-to-point setup, there's only one destination. Multiple points, I have multiple destinations. So if I put my destination, what do I put it as? Do I put it as 20.2? Because this is the public side, right? 30.3? 40.4? What do I put in? If I put all three and a packet comes in for 192.168, let's say 1.3, how does it know it needs to go to a particular place? I don't do 0, 0, 0, 0. That means send it to everyone. I don't want traffic to go to everyone. That's where MGRE uses another protocol called NHRP, Next Hop Resolution Protocol. Okay? What is Next Hop Resolution Protocol? It allows us the ability. We'll get to that question. Give me some time, I'll get to that. NHRP is a protocol that allows me to do the mapping. In the sense of what? I'll create a mapping table that says if I want to reach this tunnel IP, its public IP is 20.2. If I want to reach 3, the public IP is 30.3. This is not handled by GRE, it is done by this protocol called NHRP. All right, so now if I ping, my inside packet goes from 192.168.1.1 and it's going towards 1.3. My NHRP will map over and tell me that my public addresses for this particular packet, my tunnel source is already defined as 10.1. So I know that. My destination, by looking at the inside destination, it goes, checks the mapping table, says 192.168.1.3 is my inside destination. So the corresponding outside destination should be 30.3. So that's what the role of NHRP is. So I don't do what? Tunnel destination. Instead, I will do it based on NHRP. The way I need to configure this. First of all, change the mode. The default mode is GRE point-to-point. I'm going to change it to GRE multi-point. Then I create a mapping. IP NHRP, enable NHRP on the interface by giving it a network ID, any number, locally significant. This number is locally significant. It has no bearing on the other side. And then my mapping, IP NHRP map. If you want to reach 1.2, the public address is 20.2. If you want to reach 1.3, the public IP is 30.3. If you want to reach 1.4, the public IP is 40.4. So when a packet now comes in, the purpose of the mapping is to do what? When the inside packet is created, whatever I put in over here, whether I put in, I want to ping 2, 3, or 4, I need to put that. It doesn't find it. You need to put these numbers in because you know the public addresses. Yeah, it is static. I'm moving towards dynamic, but right now it's static. So I tell it that if you want to reach 2, 3, and 4, whichever one, the corresponding addresses are the ones that are defined over here. It needs to be done statically. But at least now I have a single interface. That's it. So if I go do this on R1, my R1 config is done. 1 second, guys, 1 sec. Sorry, guys. So this is on R1. What do I need to do on R2? Change the IP. Oops, I made a mistake. Let's go back to router 1 and put the IP in. Now let's go to router 2. What do I do on router 2? First of all, my source is 20.2. My mapping, I don't need a mapping for myself. I need a mapping for 1, 3, and 4. Copy it, go to router 2 and paste it. So these mappings are the ones that tell it how to get to a particular network. Router 3, my tunnel IP is 1.3. My tunnel source, the public header is 30.3. I need to reach 1, go through this. If I want to reach 2, go through here, 4 through here. And the last one. One, 2. I don't need a mapping for myself. I need it for 3. If you did not put subnet mask, what will it do? It will say incomplete command. On a router. Now, I've done this over here. Let's check. First thing I want you guys to check is the mapping. Show IP NHRP. This is my destination address. This is the corresponding public address. If I want to reach 1.2, this is my corresponding address. This mapping was done statically. 1.3, the mapping was done statically. Okay, So if I sit over here and I say ping 192.168.1.1, R6, the middle router, if you look at your topology, R4 to 1, there's a router in the middle, 6. He has no idea about any 192.168 network. But because of the MGRE tunnel, what's going to happen with the packet? The packet is going to be created like this. The inside header, in the routing table it says it's directly connected. It says okay. How do I reach it? In order to reach this destination, the public IP is 10.1. And my public IP is 40.4, which I've configured over here as the tunnel source. I forward the packet. It's still a GRE packet. This part is still clear. The outer header is over here. But it's a single network with what? Multiple points on it. And it will work like this. Let's check. So 4 can ping 1. It can ping 2. It can ping 3 on the tunnel, on the private addresses. But is this scalable? A couple of you guys alluded to the fact that it is not scalable, right? Why? Yes, I have a single tunnel, but look at my mappings. I need to do the mappings manually. What if I had 20 sites? I would manually have to configure the mappings for each one of those sites. Agreed? The other problem, which Kaushik alluded to, what if some of the sites have dynamic IPs? This also requires each site to have what? Static IPs. What if they have dynamic IPs? It becomes a bigger challenge then, doesn't it? Right? So how do I get around that? So MGRE, yes, it does solve one issue, but it has other issues. Two main problems with this setup. What are the two problems? Need to create static mappings, which again is not scalable. A bigger problem requires all the sites to have static IPs. Everybody agree with that? You guys understand that? Everybody, yes, no? I want you guys to understand the problem that I'm going to solve over here. This is MGRE. So what they did was they said this is not scalable. But what they also did, they came up with a concept in which they set up one of the devices as a next hop server. So let's pick R1, the central device, maybe the headquarter device. We'll set up this one as the next hop server. I treat it like a dynamic DNS server. Like, it's not a DNS server, it's like a dynamic DNS server. In the sense, it works like this. All the other sites that I have, as soon as the interface comes up, I configure them that they need to go to their next hop server, which is located at, and in order to reach it, his public IP is 10.1. Yes, R1 needs to have a static IP. But at the same time, what happens is, as soon as R2 gets up, it gets an IP address, whether static or dynamic. It also has a corresponding tunnel IP. It goes and registers itself with whom? With a configured next hop server. So on R2, I'll say R1 is my next hop server. It will go and register itself. It will tell R1, hey, listen, my tunnel IP is, and my public IP is this. Similarly, this guy, when he comes up, will do the same thing. What would he do? He's also been configured with what? This is my next hop server. And in order to reach it, the mapping for it is, so everybody needs to be configured with this type of setup. I would have the same thing on R4. And all of them, as soon as they come up, will do what? Register. Now this guy over here will have the entire database of everyone, their tunnel IP and their corresponding public IPs. If the IP changes, he will re-register over here. So he keeps on getting the up-to-date IP to IP mapping, the tunnel IP to public IP mapping. Now let's say R2 wants to communicate to R3. If the site becomes unreachable, I cannot reach it. As simple as that. It's like on a DNS server. Let's say you go to google.com. Google.com has a pointer to a particular IP address. Google.com, the server goes down. The registration's still there, but when I try to reach it, it's not available. There's no magic that's going to happen. You get my point? But the registration will be there. It's not going to help over there. So let's say 2 wants to go to 3. The dynamic entry will time out in 2 hours. No, it doesn't. Unless a request comes in. So it doesn't push this configuration. But let's say R2 wants to talk to R3. How many mappings does R2 have right now? Just one, actually. The mapping towards whom? Towards the next hop server. 2 wants to go to 3. He says, I want to ping 192.168.1.3. Checks his NHRP table. He only sees one mapping, and that's his NHS. Says, okay, I don't have it. Let me send a resolution request. To whom? To R1, to his NHS. So the next hop server is used as a registration as well as a resolution server. Asking him what? Could you please tell me what is the IP address for 192.168.1.3? He says, oh, yeah, I know that. Because 3 had registered. He will tell him that in order to reach 192.168.1.3, the public IP is, so in his database over here, he's going to now get a dynamic entry. Who gave it the entry? The next hop server did. Now the entry is created over here. Now the entry is there. He can now make a request direct. So the resolution packet will go to the next hop server. The actual data packet goes directly to what? to the destined site. Does that make sense, guys? Everybody okay with that? So I'm not pushing the mappings to everybody, but I am making them available when the need is there. Anybody needs it, come to me, resolve it, get it. Just like DNS. You know, the DNS servers have all the entries for all the different websites. They didn't push it down to their clients. But if a client comes up to them, says, hey, please give me the IP address for this particular website, that particular IP address is pushed down to the client and it gets cached. This also gets cached. The timer for this or any type of dynamic entry by default is 2 hours. If you have a single NHS, it will basically be a single point of failure. You will lose the entire connectivity if your NHS goes down. Yes, you can configure a secondary NHS server, and that's precisely why I have this other R5 in the background, so I can show you how to do the secondary server. But understand the first one first, and we'll get to the second one. Good so far? All right, so do you understand this? This portion is called dynamic multi-point VPN, DM VPN. How do I configure it? Let's take a look. That's where DMVPN steps in, these two problems that I had. This is called dynamic multi-point VPN. R1, which is also acting as my next-hop server. On the next-hop server, I'll give it an IP address. Tunnel source, I'll say F0/0. I'll pick the IP address from that interface, which is 10.1. Tunnel mode, I'm going to change it to what? GRE multipoint, right? I will enable NHRP on it. And that's it. I will not do any mappings or specify on the next-hop server. I, by default, have the capability of acting as a next-hop server, so I don't need to do anything special about it. Good. What about on the clients? Let's do R2, which is a next-hop client. Tunnel source, this one has S00. Tunnel mode is GRE multi-point. IP NHRP network ID enables it. NHS. How do I reach the NHS? The mapping for it. Everybody okay with this? What would I do on R3? Change the IP, the rest remains the same. How about R4? The rest remains the same. Because everything else points towards what? The next-hop server. I don't need to do any changes on the clients. Everything is pointing towards the next-hop server. Good so far? Now, one thing that you also need to be aware of over here, which is very important. My objective over here was not to connect the tunnel routers to each other. I also wanted to run a routing protocol. The whole purpose of the MGRE tunnel is the ability to run routing. Agreed? But when I run routing, when I run EHRP on R2, R3, R4, what does the packet look like? When I set up EHRP, RIP, or OSPF, what does the packet look like over here? Let's say I'm doing it on R2. And let's say I'm running EHRP as my protocol. Remember, we saw this earlier on. The destination is 224.0.0.10. Now I'm sitting on R2. I'm sitting over here, and a packet comes in looking like this. Who do I send it to? Why? I would send it to 1 if what do you call it? Well, actually, let's say I do send it to 1. 1 would not know 224.0.0.10. This is a multicast, isn't it? So what I need to do on each device to support my routing protocols, I need to do a special mapping. IP NHRP. Map if the address is a multicast address. It's a keyword. Multicast is a keyword. Send it to 192.1.10.1. Do you understand that? It would send it there if I put this multicast mapping. Otherwise, multicast packets will be dropped. You get my point? Because I want to be running a multicast protocol over here, all my clients need to have what? A map, multicast, send it to 10.1. So all my multicast packets will be sent towards what? R1. But if I don't do this, it's not going to send it because it's a multicast packet. So now R2, R3, and R4, all three of them have sent their EIGRP updates towards what? R1. R1 receives it. R1 wants to send a hello packet back to them. He will create the packet as 192.168.1.1, destination 224.0.0.10. Will R1 send it to every one of them? The answer is no, not unless you tell it. But now, what do I do on R1 to tell it to send it to everyone? See, on R1, do I do this? IP NHRP map multicast 20.2. I don't have their addresses because these might be what? Dynamic IPs, right? So rather than doing this, no, not 0000, rather than doing this, I tell it, hey, listen, you have a bunch of different dynamic mappings in your NHRP table. All the clients would have registered to you dynamically. As soon as router 2, router 3, router 4 came up, they registered to R1 dynamically. What you tell router 1 is saying, hey, listen, whoever has registered to you dynamically, send them a hello packet. So when you say dynamic, it checks its NHRP mapping. Whoever is there in dynamic configuration, he will get a hello packet back. So the keyword dynamic is used over there. So now the routing updates will go to any entry that is dynamically registered in the NHRP table. Now I can run any routing protocol. So I now at this point can run EIGRP. The most common protocol for DMVPN is EIGRP. Actually, 00 is good. Because now I can copy this onto all of them. Good. Ready to put it in? How does the client know to register with the NHS? Let's take a look. What did I do on the client? I told it it's NHRP NHS devices 192.168.1.1. By putting this command in, I'm telling my client that this is the IP address of your NHS server. Go register automatically. Not only that, if you don't have a mapping, go to him. So this NHS server is for registrations and resolutions. So that's how the client knows to register. Good. Have I done my routing on all of them? Yep. So let's check. So on router 1, interface tunnel 1, what I'll do over here is because I have the existing tunnel, I'll get rid of it by doing no interface tunnel. So all the config will be wiped off, and then I will do the new tunnel config. So copy it. Let's go to router 1. It will blow the old tunnel off first and then create a brand new tunnel. Right now, I don't have any mappings. Why? Take a look at my config over here under the tunnel. NHRP network ID, map multicast dynamic, and that's about it. Source and mode is GRE multipoint. But now when I go to my client, what is the client doing? I need to get rid of the tunnel though. No interface tunnel 1. It is setting its IP. It's telling it that the NHRP NHS is 192.168.1.1. Send your multicast also to 10.1, and you will notice that it has a EIGRP name relationship that has come up. So if I go to router 1 now, show IP NHRP, I have a new mapping, 192.168.1.2, was registered dynamically. And this is the public address. On R2, the mapping will be static. For whom? R1. You guys good with this? What do I do on R3? Same thing. Nothing changes. Get rid of the older tunnel interface that I had, this guy over here, and put the new one. As soon as the tunnel comes up, it will go register. So now I should have a new mapping. And because it's dynamic, I'm also going to talk to him for EIGRP because I have a map multicast dynamic. This dynamic means anyone that's in the dynamic table, send him an EIGRP update. And let's see if I'm learning the routes. 10.2, 10.3, 172.16.2, 172.16.3.0. Let's do 4. As new clients come up, they dynamically register themselves and they dynamically form EIGRP neighbor relationships and they send their routes to me. Everybody good with this so far? Any questions? This is DM VPN, but now we get into more detail about it. In here, we'll take a look at DM VPN phases. We'll take a look at phase 1, phase 2, phase 3. The protocol that we're going to use is EIGRP. We will also take a look at redundancy, which is called a dual hub DMVPN setup. One of you guys had that thing about what if one goes down? We'll take a look at that as well. What about OSPF? You can run OSPF over here, but OSPF has different issues. Let me finish the redundancy part, then I'll show you OSPF. But you need to know OSPF a little bit to be able to understand that. From the perspective of the exam and general implementation, it's going to be EIGRP. But if you want to see how to run OSPF on it, I will show you that as well. Has more issues than EIGRP does, but I'll show you that. Good so far, guys. Everybody okay with this? Let's take a short break because this is a good time to take a breather, take a look at it, take the stuff in, and then we'll go and take a look at EIGRP phase 1, 2, and 3, redundancy, and if you want, if you get a chance, we'll also do OSPF as a routing protocol. Good. So it is 7:55 right now based on our reference clock. Let's take a 10-minute break, 8:05. We'll come back and we'll knock out the rest of DMVPN. Break. All right, guys, back. All right, so let's go ahead and take a look at the DMVPN phases, the EIGRP, phase 1, phase 2, phase 3. First thing, let's start by looking at the hub. Do I have all the routes from all the different spokes? Yes, I do. I have 10.2, 10.3, 10.4. I have 172.16.2, 3, and 4. Everybody happy with that? This is what my topology looks like. I seem to have all the routes from R2, R3, R4. I have not touched R5 yet. Remember, I'm keeping that as my backup site. Correct? But one thing that you'll also notice, which I haven't shown you yet, is if I go to any of the other sites, let's say I go to router 2, and I do show IP route EIGRP, I only seem to see site 1. I don't see 3 and 4. If I go to 3, I see 1. I don't see 2 or 4. If I go to 4, I see 1. I don't see 2 or 3. Why is that? What do you guys think that's happening over here? Routing is running because I'm getting certain routes. The hub is getting all the routes, but the spokes are only getting the hub routes. What could be the problem over here? Good old split horizon. If you think about it, on the hub, all the traffic, all the routing updates on router 1 are coming in from the tunnel interface. It's running EIGRP, which is the distance vector routing protocol, and it has the split horizon feature turned on. From CCNA, do you guys remember what split horizon does? If I receive an update on a particular interface, I will not send the update back on the same interface. Right? Because they think it's the same, they should be able to talk to each other, they should be on the same interface. But over here, everybody's only communicating to the hub. So that's an issue. So for EIGRP to work properly in this type of setup, the first thing that I need to do over here is to do what? Disable split horizon. All right? How do I do that? Where do I do it? I do it on the hub. So let me note it down for you guys. As all the routes, all the spoke routes are being learned via the tunnel interface, not as, I'll just say, all the spoke routes are learned via the tunnel interface. In EIGRP, split horizon feature is turned on. It prevents routes learned from an interface to go back on the same interface. This prevents spoke routes from getting propagated to the other spokes. So what's the first thing that I need to do? First order of operation is to turn off split horizon on the hub. How do I do it? R1 interface tunnel 1, no IP, split horizon, EIGRP, and whatever the AS number is. That's the first thing that I need to do to get all the routes to everyone. So if I go to router 1, disable it, it will reset all the neighbor relationships. And as soon as the neighbor relationships are set, I go down over here, I should see all the routes now. On 2, on 3, and on 4. Good so far? So what's the first thing that you do over here? You disable split horizon for EIGRP on the hub. Otherwise, you are not going to see the spoke routes on the other spokes. Yes, yes, please. All good. All right. Now let's take a look at the phases. I want you guys to pay attention to the next stop. What is the next stop for all these routes on router 4? What's the next stop over here? R1, which makes sense. Why? If you take a look at this, router 2 sends all the routes to whom? R1. R1 is the one that forwarded the packet to whom? R3. Same thing over here. He sent the routes over here. Let's just choose a different color. So when R1 is propagating the routes to everybody, they're getting it with the next hop or what? But that's an issue. Why is that an issue? It's not an issue, but it's a feature. It's a way it works. If I want to go from 4, let's say I want to ping 10.2.2.2. I'll do a trace to 10.2.2.2. Where's the packet going to go to? It's going to go to R1. Why? The next hop is R1. It checks the next hop resolution table, NHRP. Says in order to get to 1, go to 10.1. So if I do a trace, I want to go to 2, but it goes to what? 1. And from 1, it goes to what? 2. If I do it again, 1 to 2, 1 to 2. That means if you look at your topology, I'm going from Sydney to New Delhi. But in order to go there, I first go through Dubai. So I come to Dubai and then go down to New Delhi. But the mapping is only if I want to go, you're right, but that's if I do the correct ping. If I do a ping or a trace route for what? 192.168.1.2, then it says, oh, I don't have a mapping on the 192.168. It's the same network, right? It says, let me go to the hub and figure out how to get there. It is going direct, but because I am trying to go to 192.168.1.1, but when you look at your routing table, what is it trying to map to? The next stop. The next stop is pointing to 1, so it's not going to go direct over there. because the next hop is 1. If it was on the 190, anything on the 192.168 network, any address on this 192.168.1.0 network, I will check my NHRP table. All right? But because this is not on that network, it's where? Where am I trying to go to? 10.2, I check my next hop. What's the next hop? It's not pointing to 1.2, it's pointing to 1.1, so I'm going to send the packet to 1.1. Why is that happening? Because router 2 send the route to whom? Router 1. At that point, the next hop for 10.2 was what? But then when R1 send that route to whom? To 4, that route now has the next hop of you get my point. So now when he wants to go to him, he's going to try to look for the next hop of 192.168.1.1. That is correct. That is correct, because they're all on the 192.168.1.0 network. They are on the same directly connected network. 10.2 is not. Which might be fine, which might be okay, because you might want centralized control. If you want centralized control, where you're controlling what traffic goes from spoke to spoke, where? On the hub, this is the way to do it. You understand that, Tariq? So it's not necessarily a bad thing. It is a way it's doing it. Maybe it is exactly what you want to do, because you want to control what traffic goes from one spoke to the other. But in terms of traffic efficiency, it's not very efficient. Why? Let's follow the path just over here. If I follow the path, I want to go from 4 to 2. What's the path it's going to take? It goes to 1 first. So it goes to router 4 or router 6, which is the physical path, goes to router 1. Router 1 says, oh, in order to get there, you need to go to 2. So it comes back to 6 and goes like that. It's not efficient, but maybe that's what you want, because you want to control traffic where? On the central location. Maybe Dubai is your headquarters and it wants to control what spoke traffic talks to what. If that's the case, this is what you want to do. And this is phase 1. In this phase, all traffic from spoke to spoke should go through the hub. This allows you to control what traffic from one spoke should go to another spoke. Does that make sense, guys? Everybody okay with this? This is phase 1. This is exactly phase 1. EIGRP is in phase 1 by default. So you don't need to do anything special. EIGRP is in phase 1 by default. Understood? No special configuration required. Phase 2. In this phase, you would like spoke to spoke traffic to go directly from spoke to spoke. The efficient way of doing it, not necessarily the control way, but the efficient way to do it. You will change the routing protocol behavior to accomplish this. what was the cause of it resolving the next hop as 1? The cause of that was when router 2 sent its update to router 1, it changed the next hop, right, to itself, and then sent it to 3 and 4, and vice versa. So any router I go to, whether I go to 4, next hop for all the routes is 1. 3, all the next hops are 1. 2, all the next hops are 1. So if I go to 4 or 2 or 3, anywhere I go, and I do a trace 2 hops away, you guys see that? If I go to 2 hops away. Why? Because of this next hop getting changed. So one of the things that you can do is on router 1, on the hub, under the tunnel interface, you can tell it, don't change the next hop for EIGRP 100. So what does that do? That tells EIGRP, listen, if the packet is coming, the route's coming in off an interface, going back on the same interface, don't change the next hop. So if the next hop came in as 1.2, 10.2 is reachable via 1.2, leave it as 1.2. What's the effect? Now if I go over here and do show IP route EIGRP, guess what? 1 is via 1, 2 is via 2, 3 is via 3. And same thing at the bottom. You guys understand that? That's phase 2. What will happen now if I do a trace route? Now I'm resolving to what? What's the next hop for 10.2.2.2? This guy. Direct. If I go to something that I have not resolved before, let's try 3. It will go to 1, but just to resolve. The next packet after resolution is direct. So now I'm no longer going through the hub, I'm going direct. The first packet goes to NHS for resolution. Because at that point, for 3, I did not have the next hop address, the public address for 1.3. That's why it went to R1, just to resolve it. Notice it does not show you 2 hops, it just still shows you 1 hop. Just like when you go on the internet. Let's say you want to go to google.com, right? Where does your packet get sent to first? To your DNS server to resolve, right? Before it sends the actual web packet to google.com. Same concept over here. I'm going to 1.1 just to resolve who 1.3 is, and then I go direct. Everybody okay with this? All right, good. So that is phase 2. So phase 1, hub and spoke. All traffic goes through the hub. Phase 2, traffic from spoke to spoke goes direct. What did I tweak? The routing protocol. So in EIGRP, what did I do? On a router 1 again, under the tunnel interface, no IP, next hop self EIGRP 100. Understood? Now let's do 3. 3 and 2 are very similar. in the sense that both you would like spoke-to-spoke traffic to go directly from spoke to spoke. But you won't change the routing protocol in phase 3. You will use NHRP to do a redirection to cause the traffic to go direct. So even though your hub will be your next stop, I will override the hub as the next stop by using NHRP redirects to accomplish this. Let me explain. Let's go back to phase 1. Interface tunnel 1, IP next stop self, EIGRP 100. So I'm going back to phase 1 as if I'm doing phase 1 over here. Show IP route, EIGRP, everything is pointed to 1, right? Trace route 10.2.2.2. Now I want to do spoke to spoke, but I don't want to tweak my routing protocol to do it. I want to do it in a better way. I want to do it based on NHRP. So rather than tweaking my routing protocol to do it, I'm going to use NHRP to do it. How? When the packet over here from 4 goes to R1, R1 will send the packet to 2 because it receives a packet for 10.2, it checks its own local NHRP mappings, it says I need to go to 2. But at the same time, you can configure R1 with what is known as NHRP redirection. R1 happens to know all the different mappings. It knows that 10.2 is behind R2. It knows the mapping of R2 is, because of the dynamic mapping, it knows 192.168.1.2 is 20.2. Through the routing, it knows that 10.2 is behind what? This guy. So what it does, it says, hey, listen, why is 4 sending me traffic? Well, he can get to this guy directly through 20.2. So what he does is, it lets the first packet come to R1, forwards the data packet to R2, but at the same time, he creates a new mapping. He tells him, hey, listen, if you want to get to 10.2, don't come through me, go directly to the public address of 20.2. He sends him a redirect. He creates an NHRP cache for 10.2, in which it says 10.2 is reachable via 20.2. So I don't need to change anything with what? My routing protocol, NHRP will do it. But I need to turn on this NHRP redirection to be able to do that. So the first packet goes to the control plane of R1 or just the first packet goes through completely through R1, so data plane. So the first packet in phase 3 is forwarded through the forwarding plane, the data plane. But then it gets overwritten in the sense that R1 will send the NHRP redirect telling it, hey, listen, go direct. All right? And it does override your Ceph. The NHRP redirection will override your Ceph, telling it to go direct. All right? So how do I do it? I will go to router 1, which is my hub, on there, IP NHRP redirect. Good. But by just doing this doesn't mean anything, because when I do the NHRP redirect and I do a trace, see the first 2 packets going through there, that's okay. But I keep on doing that. The reason for that is when I'm doing this, the hub is sending me a NHRP redirect. R4 gets a redirect. but you need to turn on R4 the capability of listening to the redirect. If you don't turn on the capability of listening to the redirect, it will just drop the packet off. It ignores the redirect message. So what do I need to do on R4 to accept that redirect message is under the tunnel, tell it to take the shortcut. IP NHRP shortcut, which basically tells the spokes, if you get a redirect message, put it into your NHRP table and go direct. All right? Same thing over here on the other spokes. So in this case, the config looks like this. On R1, IP NHRP redirect, R2, R3, R4. All right, so now let's take a look at it. I've done that. Let's go to 4. Remember this trace route? First one goes over there, gets a redirect. Goes direct. You look at your routing table, still pointing to what? 1. But it has a cache which overrides. So now I have a cache for 10.2 going directly to this guy. So the cache is overriding my routing. The reason it's better is more efficient because the cache is faster to check than the routing updates or routing table. So 2 and 3 are very similar to each other. The difference is in the way it's actually handled. One is done through the routing protocol, the other one is done through the NHRP cache. I just said that, Richard. 3 will be faster because it's based on the cache. There's another advantage of this. The other advantage is now, notice over here right now, I'm getting all the routes 2 hours by default. Now, the other advantage it has is, let's say I don't want these guys to know about the exact routes. I can, on router 1, also do a summary. So what I can do is I can go over here and I can do a summary address. Don't worry about that on the security exam, but in real life, I can put a summary saying any 10 network come through me. By doing this, I'm sending just a summary address to whom? To my spokes, their routing table will just have this. Although they have one route, they will actually go to the appropriate routes direct. First time round like this, and then the NHRP redirect. So although I just have a single route in the routing table, I'm still using direct paths to the spoke to spokes, which is not possible with phase 2. Phase 2, if I want to do this, I cannot summarize it. I would need to send them all the routes. So even with the summarization over here, I can also do a summary for the 172. So now if you take a look at your routing table, it's very small. But I can still reach either one of them direct. First time around, get the redirect message, go direct. Although I have no idea where these actual routes are. So that's the other advantage that you have with phase 3 is the ability to summarize. You could not do summarization with phase 2. If you did summarization, all the traffic would go through the hub. Then it would no longer be phase 2, it would be phase 1. Clear? Yes, yes. In order to do it, it's right here. Very simple to set up. I just want you guys to understand it. IP NHRP redirect on the hub, IP NHRP shortcut on the spokes. That's phase 3. So if you take a look at this, phase 1, phase 2, and phase 3 are done. Oh, I have to do another thing over here. Which is simple, that's not a big deal. Now, redundancy. Somebody said that earlier on. What if the NHS goes down? You need to set up a backup NHS. That's why I have this guy over here, R5. I'm going to use R5 as my backup NHS. How do I do that? The way you set up your backup NHS, I've done one already. R1 is already up and running as an NHS. I need to have a static mapping between the two NHS servers. Remember how we did the MGRE with the static mapping? Do that between R1 and R5. Okay, but before that, what I would do is I would go to router 1, which is the pre-configured or the already configured NHS, copy the commands, put it into Notepad, change it for the other one. He is 1.5, the rest remains the same. Summary address, I'll keep it the same because it's the same type of setup. The rest is all the same, just change the IP. But what you need to add over here is a manual map for the other guy. IP NHRP map 192.168.1.1 10.1 IP NHRP map multicast to 10.1. So router 1 and 5 should do a manual configuration to each other. So copy, go to router 5, set it up. I also need to do the same thing on R1, a manual map towards R5 now. IP NHRP map 192.168.1.5 is 50.5. IP NHRP map multicast to 50.5. Because this is a manual mapping, I need to do it manually. I'll put that also over here for you guys. This was on R5. And then I need to run my routing protocol over here. And it's done. So R5 would be done based on this. R1 and R5 now would have a neighbor relationship. So this is what you need to do on the hub sites. Same exact thing that I had on R1, copy paste it, just add a manual map towards the existing hub. On the existing hub, add a new map towards the new hub. What about on the clients? Whatever you had done for the first hub, you would need to do the same thing for the next hub. So these are the three commands that you generally put in for one hub. You're doing the same thing for the other hub. On 2, on 3, and on 4. And my backup NHS is completely set up. So if you go to 5, I have all the mapping, all the, what do you call it? All the different relationships up and running. Now if R1 goes down, I can simulate it. Shutdown of R1. My devices will continue to work. Because I have the other guy still in place. Because I have 2 NHSs now. And these are the steps that you need to do to make it work. Basically, I copied this from the first tunnel, just added the last 2 maps, the manual maps to each other. It's not a primary and secondary file, that's 2. So it'll send the request, the registration to both. It's going to send the resolution to both. It's going to get the routing update from both, but then the thing is, it's going to always use the NHRP, the table, to go from spoke to spoke. So at that point, it really doesn't matter what the hub is doing. If you want to pick one as the primary and the second one as a secondary, you tweak your routing metrics, the interface metrics for EIGRP, to select one as a better server than the other. By tweaking the EIGRP metrics on the interfaces. Got it? So that's your backup as well. Any questions? Good. Let's see the next thing that we need to do over here. So this part is done as well. Encryption using IPsec. So all this MGRE part is just to have the connectivity over there. It's great, it's scalable, but the problem with it is clear text. Right? So do you guys remember how I encrypted the tunnel earlier on? Help me out with the steps. Do you guys remember how I did GRE over IPsec? Help me out, guys. Come on. Wake up. Phase 1. Now over here, because these guys can have dynamic IPs, I'm going to put 0000. Why? I don't know what their IPs are going to be. Because these could potentially be dynamic IPs on the public side. A better way of doing it is by using certificates, but we haven't done that yet. We'll do that later on. Phase 2. phase 3 or step 3. Oh, by the way, because I'm doing what? GRE IPsec over here, I'll say mode transport. This is where mode transport is most commonly used. And the last thing, that's it. As soon as you do that, it'll encrypt all the tunnels. You need to paste this config on all the different tunnels. By doing that, you're basically saying all traffic should be encrypted, leaving the tunnel. So copy it. Let it come back up. There you go. The enable licenses are starting to come back. Oh, this is. Two, 4, 5, and there's 3. That's encryption as well. So encrypting your MGRE tunnel as well. Now, this is what you need to do in terms of the security part of it. Everybody good with this? At this point, I have covered everything that you need to know. Not the NAT part, but LAN-to-LAN IPsec tunnel, GRE, GRE IPsec, SVTI, and DMVPN. This is where we're at right now. If I had to, this is the entire VPN section. So this part mostly done, this part almost done. This, DMVPN is completely done. Next week, I'm planning on finishing off on these 3 for sure, and probably finish up on IKE V2 as well. And the following Saturday, we'll be done with Flex. So VPNs will be done. That's the plan. Now, one last thing. Again, this is not from the exam perspective, but one of you guys wanted to see how to run OSPF on the tunnel, right? Again, recommended MTU size is about 1420. In terms of adjusting it or changing it, that depends on the applications that you're running. Every application that you're running would have its own MSS. The recommendation that Cisco has, if you change the MTU size to about 1420, it should handle most of it. But that's not from the exam perspective, they don't care about that. But for real life, you want to set it to about 1420. Now, coming back and how to run OSPF over here, by default, OSPF does not run well with the tunnel interface. Why? MGRE, although it's multi-point from the perspective of the tunnel interface, OSPF still treats it as a point-to-point tunnel. Because OSPF treats it as a point-to-point tunnel, it cannot have multiple neighbors on it. So it will flap the neighbor relationships as soon as you start configuring it. Let's do that real quick over here. I'll get rid of EIGRP. And just copy this. So EIGRP is gone. Instead, I want to run OSPF. Let me show you how to do that. Router, OSPF1, network. This will work for all the 5 routers. So I'll go to router 1, 2, 3, 4, and 5. Let's see this. See this? It's going to go up, down, because I can only have one neighbor on a point-to-point circuit. OSPF treats an MGRE tunnel interface as a point-to-point circuit. Hence the issue. What's a fix? 2 fixes. OSPF on the MGRE tunnel interface. Change the, if you want phase 1. Remember phase 1 is hub and spoke? If you want phase 1, change the network type to point to multi-point on all the tunnel interfaces. Interface tunnel 1. If you don't understand OSPF network types, don't worry about it. Copy 1, 2, 3, 4, and 5. By doing this, if you go to any of the routers, let's say router 4, do show IP route OSPF, give it some time, everything will come from 1. Remember that hub and spoke type of setup? Eventually everything will come. 3 and 4 will also come. Either through 1 or through 5. This is phase 1. If you want phase 2, which is direct, it's a little bit more complicated. Change the network type to broadcast. On all the tunnel interfaces. Set the spokes with an interface priority of 0 so that they do not become DR BDRs. So this is on the spokes. All right, let's do this first. on the spokes. And then I would go ahead and change the network type to broadcast on all of them. This is phase 2. Phase 3, it doesn't really matter. Either one is fine because it's always relying on NHRP to do the forwarding. So it really doesn't matter which way you do it. Either way is fine. So now if I take a look at show IP OSPF neighbors, it'll go through that 40-second wait for EdgeRP to come up. Oh, sorry, OSPF to come up before it does it. But if you take a look at the priorities are zeros for the other 3. So they will not become DRBDRs. There you go. The neighbor came up. If I go to 4 now, 5 is through 5, 3 is through 3, 2 is to 2, and 1 to 1. This is your phase 2, spoke 2. But again, you need to work with what? The network type to make it work. Otherwise, it doesn't work. You would need to know OSPF a little better for you to be able to configure OSPF on MGRE tunnel interfaces. EdgeRP is simpler. That's a recommended protocol for MGRE. Done. So now I want you guys to tell me your names, your email addresses are there or not. You just check 1 second. If your email address is not here, let me know so I can add it. These are the people that I'm going to be sending the workbook and the notes to. Find your name. If it's not there, let me know. Manik, you're not there? Oops, sorry. Fahad, you're not there? Should be. Check your names first before you put them in. You guys check your name. Fahad, you're there, man. Prithvi, you're there, man. Okay, hold on a second. Isam, you're not there? Okay. Okay, I got Isam. Prasad, I don't think you should be there. So I'll add you. Maybe around the 18th, but I'm not sure yet. Ahmed, you're there or no? You should be, man. Ibrahim, you're not there? Or are you just doing it just to make sure? Sam, I added you. Prasad, I added you. Did I forget anything? Anybody now? Check again, please. All right, then. I'll send you the notes, and I shall see you guys next Saturday, same time. Take care, guys. Yeah, both notes, yesterday and today. Coming up in another, thank you, Ahmed. RNS, another 30 minutes, man. Bye now. Take care.